And hopefully it will give some insight into what invertible neural networks are and how they relate to standard neural network models and normalizing flows. So first of all, we've looked at this problem in the context of inverse problems. And an inverse problem is essentially a task where we are trying to reconstruct some input from a measured output. So we have some measurement of some measurement of some sort, and then we're trying to reconstruct the causes of this measured effect. So these are commonly defined in the context of some initial forward problem or something. And these forward problems are commonly considered a data generation model, where we consistently consider this extra term epsilon here, which is a random variable. So we're assuming that the measurement has some sort of measurement noise, or there is some sort of uncertainty related to the measurements. So Hadamard first posed these criteria for what we can consider a well-posed problem. And a well-posed problem is a problem where we can be sure that there is a solution to the problem, which is the existence criteria. The second criteria is uniqueness, meaning that the solution has to be unique. And the third criteria is that the solution has to be stable, meaning that the inputs and outputs should continuously depend on each other. So what does this mean? Well, the defining feature of these inverse problems is that they're fundamentally ill-posed. So if any one of these criteria is not fulfilled, then the problem can be defined as an inverse problem, or we call it an inverse problem. And here we see that adding noise means that we can kind of, in this illustration at least, kind of fall outside of what we consider the actual solution space that we're looking at. So inverse problems are very common in imaging, especially image reconstruction tasks. And we name a few like denoising, upscaling, deblurring, which are kind of similar. In painting is a very common inverse problem in imaging as well. In addition, we have the more specialized inverse problems where we look at where we have X-ray tomography or ultrasound reconstructions of images and seismic inversion. And the observation is that most supervised learning tasks can be kind of framed in this context of inverse problems. So they're very similar in the way that they're formulated. So the background for inverse problems come from integral equations. And an integral equation can be classified in two main groups. The first order integral equation, which we call homogeneous, and the second order integral equations that we call inhomogeneous. This can look a little bit intimidating. However, these kernels, this W part here, it turns out that these form what we call Hilbert-Schmidt integral operators, given that these the domain here, these S's are a connected subset of some d-dimensional Euclidean space. Or it doesn't have to be Euclidean actually, but so it turns out that these types of equations are kernels of compact linear operators. So in the finite dimensional case, we can simply consider these as matrices, and we're basically working in discrete cases in deep learning. So this is how we think of how we can work with these types of problems. So operators with a kernel function on this form here. Where we have this particular form where it subtract S from T and integrate over that. They're called convolution operators and are probably familiar to most of you. So their general form is like this, and their eigenfunctions are the complex exponentials, meaning that they act as a diagonalization. The Fourier transform actually acts as a diagonalization of convolution operators. In addition, the adjoint operator is commonly applied in convolution layers, as we know, or in a linear combination. Also, the discrete form can be represented like this, and this gives, with circular boundary conditions, that gives a circular tuplets matrix. So solving these linear inverse problems is usually done by methods that we all probably know. We use least squares methods via the pseudo-inverse, or via the singular value decomposition, to be precise, and then we can reconstruct our inputs. For inhomogeneous problems on this form, we instead can apply something called the Louisville-Neumann series, which if this lambda term is less than the norm of the operator, we can uniquely find or reconstruct the inputs using this series. The problem is that this series is obviously infinite, or in many cases infinite, meaning that you have to truncate at some point, but generally that's not a problem. So some of the issues with solving these linear inverse problems is that we have some symptoms. We have two problems with similar symptoms. One of which is underdetermination, where we have some explicit information loss, where the dimensionality of the measurement is less than the dimensionality of the causes. So this is a very common inverse problem. In addition, we have this problem of conditioning. Given that we have a stable inverse problem, meaning that there is a continuous map between the inputs and outputs, it doesn't mean that the solution is stable in a practical way. Meaning that the mapping can be highly sensitive to the differences in the measurements. To see why this plays such a big effect, we can look at the variance of these least square solutions using the singular value expansion or singular value decomposition. So the variance of a least square solution is essentially given that we have a Gaussian error term, is given by this term here, and we see that these funny-looking sigmas are. We denote that, we use this to denote the singular values. The thing to note here is that when these singular values, if some of these singular values go to 0, it implies that the variance goes to infinity. And this is obviously problematic because then we have infinite variation in the reconstructions. So Per Christian Hansen actually took this a little bit further and said, for convolution operators, this will always be the case due to the fact that they have this the coefficients of the diagonalization means are basically the Fourier coefficients, and the Fourier coefficients will always go to 0 for any kind of infinite dimensional or function in functional space, meaning that convolution are fundamentally unstable. So an illustrative example of this comes from a deblurring task where we simply have an image that we blur with this convolution operator W, and our task is then to kind of reconstruct the image X, given that we have this affection by noise. So in the middle here we see that the image is simply blurred, and in the top row we see the forward operator. So the left side is the original image, and then the blurred image, and then we add a very, very minor level of noise. As we see here, the variance is 0.01, or this squared, so the standard deviation is 0.01. And we see that when we try to reconstruct this using a least square operator, we get a lot of noise. It's almost impossible to see that the image is is anywhere close to the original. So the way that we solve this is using what we call regularization, which is commonly some penalty term to an objective function. And in the Bayesian in the Bayesian inference, from the Bayesian inference point of view, this corresponds to some sort of prior distribution on our noise variable epsilon. So for Tikhonov or Ridge L2 regularization, this corresponds to a Gaussian prior, or for Lasso, it corresponds to a Laplacian prior. And the effect of these the regularization, or the most canonical form of regularization, the Tikhonov regularization, can be seen here, where we see that it effectively smooths the singular values, meaning that for singular values close to 0, you smooth out the effects slightly, so you don't actually get these issues. So we can see how the effect of regularization is here on this deblurring example, where we see that with different levels of Tikhonov regularization, we can achieve better reconstructions. Of course, this also diminishes the quality of the reconstructions where we are not affected by noise, or it smooths the solution space. So these are much more similar. The more regularization you apply, the more you smooth out the image, and the more you remove the noise, if there is any noise. So nonlinear inverse problems are much more difficult to approach and pose a serious challenge. However, obviously, neural networks have this very nice and attractive property called universal approximation, and this makes them a very powerful method for approaching inverse problems. So the limitations of neural networks is that the dimensionality of the network can be arbitrarily large. They can be computationally expensive to train. They're basically black box models with poor inference capabilities. However, this is one of our research challenges. Furthermore, they're generally discriminative. So there's no measure of the uncertainty of the reconstructions, yes, it generally provides no measures of uncertainty, which is another research challenge for the visual intelligence group. So, and finally, the model can exhibit high level of instability, which is what we kind of introduced a little bit earlier. However, neural networks have this very special type of instability, or in deep learning, we have different challenges. So the most pervasive source of instability in a neural network model is adversarial perturbations, where we're essentially looking to kind of find the worst case perturbation to kind of offset the network as most in the worst way possible. So for inverse problems, we can kind of consider these adversarial perturbation vectors as a worst case representation of a stochastic noise element. So the nice thing in the context of these adversarial perturbations is that we can kind of consider them a stricter form of or robustness to these adversarial perturbations can be considered stricter than any kind of robustness to general stochastic noise. However, it's not always very clear how to estimate the conditioning, the robustness of a deep learning model. However, we can use these adversarial perturbations to compute an adversarial condition number, where we basically use gradient descent to find the worst possible perturbation vector for a model, and then compute this adversarial condition number. And these provide good estimates of the conditioning of a neural network. And this method of doing this is kind of inspired by the work of Vegard Anton at UIO, who's done a lot of work on inverse problems in deep learning. So the standard method of regularization against adversarial attacks is adversarial training. And adversarial training is where you find one of these perturbation vectors and then you retrain your network using this to basically to not have such a big effect on the outputs. However, there's an interesting alternative that was provided by Sis et al. In 2017, which is called Parseval regularization. And Parseval regularization is essentially trying to make the weights of the network, these W's, orthogonal or unitary in the case of complex valued inputs. This encourages the spectral norm, i.e. the Lipschitz constant, to be approximately 1. And this simply means that the function has the slope of the approximated function is close to 1. So this method of regularization proposed by Sis, this Parseval regularization, has some interesting connections with a topic called learning dynamics. So very early on in the history of deep learning, there was a lot of focus based or a lot of focus was put towards making sure that the gradients of the loss propagated well throughout the network. And this was first introduced, or one of the first methods of ensuring this was proposed by Bengio in 2007 with this greedy layer-wise unsupervised pre-training. And this is basically what you do is that you have a layer, psi1 here, that like, so you take your network and you train one layer at a time by computing its output, and then you append a decoder to basically reconstruct that input for the first layer. And when this is well trained, or when the difference between the inputs are similar, inputs and the decoded inputs are similar, then you train the next layer, and then you use the find another decoder and decode your input again, and you continue doing this until you've trained all or pre-trained all the layers of your network. So this uses kind of an autoencoder approach where you do one layer at a time. And then what you do at the end is that you just throw away all these decoders and use that as a weight initialization process. More recently, there's been some work on something called dynamic isometry, where Pennington, Schoenholz, and Ganguly showed that this can be achieved, that optimal learning dynamics via dynamic isometry can be achieved by initializing all the weights to be orthogonal. So there's this interesting link here between learning dynamics and Parseval regularization. So how do we approach inverse problems with inverse problems of image reconstruction with deep learning models? So some of the criteria or some of the things we will focus on is that we want our model to be stable and robust to particularly to adversarial attacks. We also want to minimize the hallucinatory artifacts, meaning there's been a lot of talk about image reconstruction tasks where you're trying to reconstruct some image from some features or lower dimensional space. And in some of these cases, you see that a reconstruction can artificially add elements that we as humans would consider very strange. I mean, in terms of medical imaging, for instance, and X-ray tomography, for instance, you can see sometimes that a model can kind of artificially add an extra rib. And we want to minimize these types of effects. In addition, we want to maximize some relation between inputs and outputs. meaning that we want the inputs and outputs to have, like, to contain most of the same information at least. Ideally, that we would have some sort of metric for the causal relationship, but of course, information theory provides a good way of kind of measuring this. So one of the ideas is to kind of learn the forward and inverse mapping, both at the same time with two-way learning. To this extent, to this kind of, or towards this kind of goal, we first looked at what's called supervised autoencoders, which are basically autoencoders with an extra term on the latent space, where you want to kind of supervise the autoencoder in some way. And this can be used in place of a normal neural network. And some work has gone into looking at the effect of these supervised autoencoders, and they have some nice properties. In particular, they display inherent regularization, which improves robustness. They provide tighter upper bounds on the generalization error, and they maximize the lower bound on mutual information between inputs and outputs. This last property is actually a general property of autoencoders. But this property is obviously retained for supervised autoencoders. So the issues with applying a supervised autoencoder is that, especially in the context of this two-way learning approach, where we're trying to learn both the forward and inverse operator, is that the final model is not a bijection, meaning that there's not this very strong, the strong relation that we want between our inputs and outputs is not necessarily there. Or it's not guaranteed, at least. So one of the issues that we can face is that the model will approximate the inverse of the encoder rather than the inverse of that we want, the inverse problem. And there's no dependence between the parametrization of the encoder and decoder networks, meaning that they don't communicate in any way. There's no way of extracting the parameters of the decoder from the encoder and vice versa. And it does not directly address any kind of instabilities caused by adversarial attacks. It does improve robustness in general, but it does not improve robustness to adversarial attacks in any meaningful way. So the question is it possible to do better than this for two-way learning tasks? So an invertible neural network is an enticing approach where, like, if we have a network and we know that we can invert this network, we can use this for these types of tasks. So an invertible neural network is simply a neural network where if the network is a diffeomorphism, meaning that it's continuous and it's differentiable, we say that this network is an invertible neural network. So the question is, how do we construct these invertible neural networks? And the interesting thing is that normalizing flows actually apply invertible neural networks to do density estimation and probabilistic estimations. So these types of models are actually around, and I think there's been a talk already on normalizing flows. We won't go too much into it, but these are the nice thing is that these normalizing flows can be used to construct invertible neural networks, and in turn, an invertible neural network can be used to construct a normalizing flow. The most common method, or one of the original methods of constructing an invertible neural network or a normalizing flows is via these special types of layers called coupling layers, which were popularized by DIN in 2017 with affine coupling layers in a model called real MVP. And the affine coupling layer is essentially it can be kind of thought of as a subnetwork where we have, or two subnetworks, where we basically have a neural network predict some parameters for transforming half of our input space. So we basically slice the dimensions of our input in two, and we let one half affect the other half. And then in the next layer, we do the opposite. So we let the transformed half affect the other half. And the nice thing about this approach is that it's bijective. Given that you have one half that's untransformed in every layer, you use the same network to kind of find the same parameters, and you can basically invert the layer. It also has a triangular Jacobian, which simplifies the computation of the change of variable formula, which is the central part of a normalizing flow. So this is very, very easy to compute. So invertible neural networks with coupling, I kind of discussed or kind of talked about it, but here's a figure showing that we split the inputs, and then we let some part of the input affect another part of the other part of the input, and then we do this back and forth ad nauseum. One thing that's important to note is that you can, like for each one of these double blocks, you can permute the inputs. If you have some sort of, you can just draw uniformly some permutation and then permute the inputs accordingly. So you don't have separate parts acting on each other. So an important result with these types of models is that Teshima showed in 2020, a team in Japan showed that this architecture can be used to construct universal diffeomorphism approximators, meaning you can approximate any type of invertible structure that's differentiable with this type of architecture. A very common, another common method for constructing invertible neural networks or normalizing flows in general is autoregressive structures, where we explicitly enforce a dependency where we have some sort of ordering on the inputs and let each output only be affected by a certain set of inputs. And you leave the first input untouched generally. So in 2015, Germain et al. Proposed kind of doing this in a concurrent way with masked autoencoders, where you draw a mask or you sample a mask of a binary mask for each weight in the network, which according to some criteria, so it kind of preserves the autoregressive property. So you basically preserve this dependency, which means that you can invert your architecture. In addition to that, Beerman et al. In 2019 introduced proposed an interesting approach to invertible neural networks, which uses this iterative way of approaching ResNets. Basically, what you do is like a standard ResNet block can be written in this form, and if you want to invert this, you can kind of just start with some initial guess of the reconstruction, and then apply an iterative way of solving this in this way. And if the network is contractive, meaning that it has a Lipschitz constant less than 1, then it will converge to the solution. However, it's difficult to enforce this contractive property or it's difficult, but it's possible to do, but it's computationally expensive. So invertible neural networks have been applied into inverse problems before. In particular, Ardizon et al. First proposed applying these invertible neural networks to inverse problems. So one of the cool proposals they had was how do you deal with underdetermination, right? So if you have some sort of information loss one way, it doesn't matter whatever you do, you're not going to be able to reconstruct an input from a very minimal set of outputs, or in general, it's not very easy to do that. So their idea was to augment these the outputs. Why? with some latent variables that you ensure follows some probability distribution. And using normalizing flows in conjunction with invertible neural networks, you can explicitly find, or you have a tractable distribution for P, given that you can control the distribution that you sample from here. This is tractable and everything is fine and dandy. And this is a very cool approach. There are several other variants of coupling-based architectures, some of which we mention here. However, and some of the pros of the coupling approach to invertible neural networks is that in invertible neural networks in general, is that the network architecture is guaranteed to be bijective, and normalizing flows are very powerful density estimators. Mostly, in most cases, they outperform other probabilistic methods. The downsides of using these coupling-based invertible neural networks is that they can be computationally expensive and require a neural network for each of these transformations, meaning that every time we compute the parameters of this affine transformation using a scalar and a shift, then each one of these are computed using a neural network, and this is very expensive. And in addition, they differ very significantly from standard architectures, these coupling-based architectures, at least. So what we wanted to look at was that the possibility of constructing invertible neural networks with standard architectures. So we wanted to build on the supervised autoencoder structure, and what we wanted was to kind of construct an ideal autoencoder, meaning that for each input, the encoder composed with the decoder will always perfectly reconstruct the input. And then we say that this is an ideal autoencoder. So a trivial case can be just setting all the weight matrices to be identity and all the activations to be identity, and then you trivially have one, but it's not very useful. So how do we construct a non-trivial ideal autoencoder? Well, we require that the encoder and decoder are of similar lengths. We require that the parametrization is the same, essentially. And we require that all the activations, gamma, I, are C1 piecewise diffeomorphic, meaning that they're basically piecewise invertible and differentiable. And we also, well, this is not a requirement, but the way that we constructed our non-trivial ideal autoencoder is to simply say that the weights are orthogonal. And if we then index the layers in reverse order and let each layer be given by these two terms here, then each layer will be will just unroll basically the inputs of the previous layer. So we can perfectly reconstruct our inputs. And this is a computationally effective method as well, and has this nice property with orthogonality that we saw from Parseval regularization and dynamic isometry as well. So we call this family of non-trivial ideal autoencoders for invertible unitary encoders. There are, we mentioned here, like in our thesis or in my master thesis, we basically construct some other types as well. But they don't have the same nice properties. So the properties that invertible unitary encoders have is that they're optimal with respect to learning dynamics and optimal with respect to Parseval regularization, like we talked about. And the joint parametrization removes the need for a separate decoder, which can effectively halve the number of parameters in the model, which is can be a very attractive prospect in some cases. So the difference between a standard neural network and an invertible encoder is that given a standard neural network on this form here, a feed-forward stacked neural network, is that we basically can use the transpose or the adjoint of each weight to basically reconstruct our inputs. So to construct these, we need some components. And the necessary components for constructing these unitary encoders requires that we have piecewise diffeomorphic activation and unitary or orthogonal constraints on the weights. So the activation is the simplest problem to solve. There are certain piecewise diffeomorphic activations already. Leaky ReLU, for instance, or sigmoid, or the logistic function are both examples of diffeomorphic activation. However, their range is often constrained. So our idea was to kind of construct activation functions which have this bi-Lipschitz property, meaning that we can constrain the Lipschitz constant of each activation. So we use this to kind of construct some variants of ReLU, ELU, and CELU. And we see here, how they differ. So the left three here are the original functions, and we use this kind of spline method to kind of construct these functions. This last one, this bi-Lipschitzian CELU function, has very nice properties and is also the one that performs the best. So in particular, it's monotonic. It approximates the identity at 0. It's bijective, and its domain is all of R. Its range is all of R. And we can constrain its Lipschitz constant in both directions. In addition to that, we also wanted to use softmax, which is obviously not invertible and and thus cannot be used in invertible neural networks. So our idea was that we can possibly approach finding some sort of transformation to construct a symmetric Dirichlet prior. So WISE has an approximate beta to Gaussian transformation, and given that alpha and beta are greater than 1. In addition to that, stick breaking, which is a common method for constructing a Dirichlet process in Bayesian non-parametrics. This stick breaking process allows for a beta to Dirichlet transformation. So this means that we can go from Gaussian to Dirichlet. And we show that both of these are bijective. And this transformation can also be applied to construct non-symmetric Dirichlet priors, meaning that the alpha of the Dirichlet distribution can be learned. This is something that we're currently still working on, and not something that we added in the thesis. But for our purposes, in terms of these invertible encoders, we only wanted to kind of have a symmetric or an approximation to the softmax, which was invertible. Now we move on to the parametrization of the weights. So how can we enforce unitary or orthogonal constraints on the weights? Well, one simple way of doing this is to simply not do anything and just use the architecture and let the network kind of approximate invertible or orthogonal weights by itself, using the definition of an invertible unitary encoder. And this implicitly enforces the constraints. And in effect, what this is kind of a Parseval autoencoder. And the key observation is that this is a simple way of doing something, of constructing an encoder-decoder model which has joint parametrization and which will have basically an inbuilt Parseval regularization term. And this halves the number of the parameters of an encoder-decoder model. So the issue is that this is not bijective or diffeomorphic, and it's not directly an invertible neural network. However, it can be. It doesn't mean that it's not usable. I mean, autoencoders have been around for a while for a reason. So, we in our thesis we call them pseudo-invertible encoders. In this talk, I've kind of started calling them Parseval autoencoders because it makes a little bit more sense. So we have here we see a simple experiment that we had used in our thesis, where we looked at a pseudo-invertible or Parseval autoencoder compared to a standard autoencoder on an unsupervised objective. Clearly, both of these do well. It's a very simple data sets and etc. However, we see that the pseudo-invertible encoder outperforms the autoencoder. So the question is this pseudo-invertible or semi-unitary, unitary orthogonal property retained when we train our network like this? And we had some different ideas of how to quantify this, and one idea was to compare the Gramians, meaning the self-adjoints of the weights, to identity, which kind of aligns with the Parseval objective as well. However, we see the results here. However, one thing that you have to note is that when you just initialize a weight matrix in a neural network, it will always have some notion of orthogonality due to the independence of the initialized weights. So we want to factor that part out to kind of look at, are the weights actually orthogonal? Has the network learned anything? So what we did was we sampled 10,000 matrices using standard initialization, and we computed the relative error of the Gramians with respect to identity. So we took the Gramians and compared it to the identity and found the distance or the norm between the difference between the identity and the Frobenius norm. And what we found is that these were normal. They had a normal distribution, these errors. And we saw that an interesting thing we noticed was that the decoder actually had the weights of the decoder actually became more orthogonal in an autoencoder. And however, in the encoder of an autoencoder, it moves one of the weights moves away from being orthogonal quite significantly, and the weights of the pseudo-invertible encoder basically moves towards being orthogonal for both weights. So this was a two-layer model, just to clarify. So basically, an autoencoder on its own does some orthogonal things. However, a pseudo-invertible encoder will be even more orthogonal, or basically applies this to an even greater extent. We also looked at applications of variational methods with a Parseval autoencoder. So we compared it to a standard variational autoencoder, where we wanted to kind of enforce a conditioning on the labels on MNIST, basically. So we constructed this model here, where we used we wanted to enforce that the y's follow a symmetric Dirichlet distribution, and we wanted the z's conditioned on x and y, where x are the images and y are the labels. We wanted this latent representation to be standard multivariate normal, and we used a kind of what's called a separable patch kind of method, in addition to an additive coupling, with the final activation being Dirichlet softmax. And doing this allows us to kind of condition the outputs of the probabilistic outputs on the labels, and allows us to kind of reconstruct images given labels as well. So the question is, do the networks successfully capture this joint distribution over the images, the labels, and this latent probabilistic term? Well, to check this, we computed the labels, we computed the labels and the latent outputs, and then we sampled a new set of labels and computed the reconstruction of the image. And here we basically sampled the labels to be 1, 2, 3, 4, 5, 6, 7. And the top here is the original image, and this other image is where we kept this probabilistic latent variable the same, and changed only the labels. And we see here that the pseudo-invertible encoder, or Parseval autoencoder, uses this information to reconstruct the inputs. However, the autoencoder, which is trained in basically the same way, it doesn't use any of this label information, it just throws it away. So it uses this label information to predict the labels, but to construct the image, it's not used at all. Another thing we did was to instead sample new latent probabilistic vectors, or a new latent probabilistic vector, Z. And then we used this to reconstruct our image instead. So we kept the labels the same and simply sampled the new latent vector. And we see here that this maintains the labels of the original image, but changes the shape somewhat. And I mean, this image is maybe not the best, but you see that it's quite flexible. It can kind of construct. It can fully parameterize the shape of the reconstructed images. Whereas the autoencoder doesn't do that at all. It simply outputs garbage. So the result is that, yeah, the pseudo-invertible encoder successfully captures this joint distribution, while the autoencoder fails. So the question is, can we now enforce explicit constraints on our weights? So what we did was that we used what's called matrix manifold learning on Lie groups. There's a really good source of information on this topic made by Absel, Mahoney, and Sepulcher. In addition, Casado has written a really good paper on how to do this in neural networks. So a lot of this is kind of based on this. So we have the group of special orthogonal matrices, meaning that they're orthogonal and they have determinant 1, and that only constrains the difference between the standard orthogonal group is that the determinant cannot be flipped. So we can't have it removes flipping. It only allows for kind of rotations. In addition to that, we have the Lie algebra of SO, which is the set of n by n skew symmetric matrices. And we have the matrix exponential, which is a mapping. The matrix exponential maps from a Lie algebra to a Lie group. Yeah, so every Lie group as well has an associated, or every matrix Lie group has an associated matrix manifold. And this is what we want to use to kind of enforce the constraints in our matrices. So the challenge then is how do we apply gradient descent on this group? Well, one initial idea is to simply just use the fact that you can map between the special orthogonal algebra to the special orthogonal group. However, this turns out not to be a very good solution. Why? Well, the fact of the matter is that the special orthogonal group does not have the same geometry as Euclidean space. It's a Riemannian manifold, and it has a special type of geometry that we have to kind of pay attention to. So given a point on this manifold, in this case where the point is a matrix, we might want to move in a direction on this manifold. So in this case, we want to move according to this vector here. But we see that the vector points out into Euclidean space, whereas the shadow of this vector in this visualization is a projection onto the manifold. So we want to kind of use this, and we want to kind of follow this line here on the manifold according to this vector. And this line on the manifold, or straight lines on the manifold, are called a geodesic. So we want to follow the geodesic to the next point into our update. So this means that we have to first select a direction in the tangent space of the point on the manifold. And this tangent space is every vector that's tangential to the manifold at a given point. And this is standard in Euclidean geometry as well. However, it's not exactly. It's much more free, right? So what we want to do, like once we've selected a vector, we want to project this down to this new point where we're moving in a gradient descent manner. So this is some for some people, it might be some tedious details about how we do gradient descent on the special orthogonal group. So the tangent space at identity is given by the special orthogonal Lie algebra. And given any kind of matrix, the tangent space at this, for this point, or this matrix at this point, is given by UV, where V is in the special orthogonal algebra, so in the set of skew symmetric matrices, essentially. Then, given a loss function on simply this orthogonal matrix, the Riemannian gradient descent objective is given by this. However, Casado showed that using trivializations or retractions, or a mix of both, we can simplify this or we can change this objective, or it's equivalent to this alternate objective, where instead of optimizing over the special orthogonal group, we optimize over the tangent space, and the tangent space is this shifted set of skew symmetric matrices, or it's the skew symmetric matrices that are multiplied by the point that we're at. And this gives updates on the form here, where we basically compute a direction based on the fact that we're assuming that we're in the origin of our current place on the manifold. And then we update our matrix given this computation, and then we retract that back, and then we can perform gradient descent on matrix Lie group. So here's an example of some results. This is we did some image upscaling with invertible encoder. It's very hard to see any differences here, but all these three models did quite well. However, we see that in the observations, we can see that the pseudo-invertible encoder performed the best, which is good on its own. The invertible encoder turned out to be more robust, and actually this seems little, but it's quite a lot, actually. And the invertible encoder performs slightly better on the downscaling task than the autoencoder. However, it performs slightly worse on the upscaling task than the autoencoder. So this is generally due to the inverse problem. So one of the directions is actually has some significant loss of information, and that means that this it's easy to kind of scale something down when you don't have to keep this information on the way back. So these are I also have to kind of mention that these are semi-orthogonal matrices. So there is a loss of information in these. However, we also did some experiments with full rank matrices, and these are which also had some interesting results. But we focused on this result in this talk. So the observations that we made from our results, which can be read in our master thesis once it's uploaded to Duo, is that these invertible encoders and pseudo-invertible encoders provide similar performance to autoencoder models. The invertible encoders or pseudo-invertible encoders with unitary architectures can provide better guarantees for stability and robustness, in particular to adversarial attacks. Invertible encoders and pseudo-invertible encoders can provide a reduction of the dimension of the parameter space as well, with small loss of performance. In some cases, a small loss of performance. And these models are promising in the applications, in general applications for inverse problems. And however, we would like to do even more testing, of course. So it's an interesting take and can play a part in bridging this gap between feed-forward models and normalizing flows, which also provides interesting, very broad and interesting way of doing probabilistic learning with neural networks. So further work, what we're currently working on is expanding this Dirichlet softmax transform to include learnable parameters. We're also working on orthogonal convolution layers, explicit constraints on orthogonal convolution, and we're working on invertible encoders in normalizing flows, and in particular with focus on orthogonal convolution. So that's it for me.